Hi everyone, welcome to the fourth big chapter of the statistics course. My name is Artificial Intelligence.
Its name is artificial intelligence indeed, but particle physicists call it MVA, short for multivariate analysis. In fact, MVA is just a hypothesis testing. Or if you like, MVA is a field of statistics whose goal is to find good approximations for PDFs. In particle physics, MVA is used for testing hypotheses about individual events or individual objects. This is a TT-bar event. This is a Higgs event. This is a hadronically decaying Z boson. This is a gluon-originated jet. This is a birthday party. This is my son. This is SpongeBob. Events in particle physics are characterized by a certain set of data. Information read from channels of a detector. Each event is like a photograph, and MVA techniques are used to check what is on the photos. Given the complexity of particle detectors, there can be 10 million channels easily, and therefore 10 million variables describing the event. No MVA algorithm would be able to accept this as an input. Fortunately, it's not needed, because people process the raw data about each event very thoroughly and group information from the individual channels to form objects like muons, electrons, photons, jets, and so on. Typically, MVA then comes to help to ascertain the nature of the objects. In the same way, MVA is used to test hypotheses about nature of the whole event, whether it is a Higgs event or some background. Throughout this chapter, we will use the word event to refer to both events and objects. The actual input variables to the MVA algorithms are momenta of the reconstructed objects, distances between the objects, missing transverse energy, etc. In practice, only a small subset of all reconstructed variables can be used in the test. We call these discriminating variables. Throughout this chapter, we will denote the set of discriminating variables X vector. Also, we will always test the hypothesis that the event, or the object, is signal. This will be the null hypothesis H0. The alternative hypothesis H1 will be that it is some background. Signal efficiency is the probability to accept a signal event. It is equal to 1 minus the type 1 error alpha of the test. Epsilon signal is equal to 1 minus alpha. The signal efficiency is fixed by the choice of the critical region of the test, typically by setting a cut on the test statistic. The background efficiency is the probability to accept a background event. It is equal to the type 2 error of the hypothesis test beta. Epsilon background is equal to beta. Background rejection is the probability to reject a background event. It is equal to the power of the test. R background is equal to 1 minus epsilon background, and this is equal to 1 minus beta. Tests with high power have a high background rejection for a given signal efficiency. Obviously, the ultimate goal of MVA algorithms is to maximize the background rejection for a given signal efficiency. Very often, people use ROC curves that visualize the dependence of the background rejection on the signal efficiency. ROC is an abbreviation of a receiver operating characteristic, but you will never hear this full name again. Remember just ROC and you're done. For each experiment, there's always an optimal test that provides, for each signal efficiency, the highest possible background rejection. Written mathematically, R background optimal of epsilon signal is greater or equal than R background of epsilon signal. Obviously, the integral of the optimal test ROC curve is higher than integrals of ROC curves corresponding to all other tests. This is often used when comparing different MVA methods. Note that the choice of the discriminating variables is important. The same test technique can have different performance depending on the chosen variables. Usually, more variables mean a better test, but it might not be technically possible to use a large number of variables. People try to pick a small number of variables with good separation between the signal and the background. Here, separation or discrimination power means that the PDF for the signal is different from the PDF for background. ROC curves are also used to compare tests based on different numbers of input variables. In the end, people need to fully define their test, including the choice of the test size alpha. In other words, people have to choose the signal efficiency. This choice determines one point on the ROC curve. At the LHC experiments, the point is called working point. For example, the working point can be required to maximize the signal significance. I mean significance of a test based on the collection of your events. The simplest approximate formula for this significance is S over square root of b. Let's write the expression down. Z0 is approximately equal to the number of signal events over the square root of the number of background events, and this is equal to the square root of the total number of events n times the fraction of signal events times the signal efficiency over the square root of 1 minus the fraction of signal events times the background efficiency. As explained in a previous video, such an approximation holds in the large sample limit, when you have enough data to approximate the Poisson distribution for the number of events with a Gaussian. Now let's recall the starting point for the previous chapter about hypothesis testing. The Neyman-Pearson lemma states that the critical region providing a test with the highest power is where the ratio of PDFs for signal and background is the highest. In the loose terminology of statisticians, this ratio is called the likelihood ratio. So, the likelihood ratio provides the optimal test for a given set of discriminating variables. Mathematically written, lambda of x vector is equal to f of x vector given the signal hypothesis over f of x vector given the background hypothesis, and this is greater than constant c sub alpha. Recall that c sub alpha is a constant that determines the size of the test alpha and, in turn, the signal efficiency. In the chapter on hypothesis testing, we were concerned about incorporation of systematic uncertainties into the test. In the current chapter, we will forget about systematic uncertainties and we will focus on a different important issue. We don't know the PDFs in particle physics, and therefore we are unable to construct the likelihood ratio. Typically, we have just Monte Carlo simulation, which are samples of events sampled from the PDFs. But we don't know the PDFs themselves. For sure you say, why not to approximate the PDFs by histograms of the Monte Carlo events? We could do it, if we had enough events. Imagine you have two discriminating variables. Then the number of bins of the 2D histogram is a product of the numbers of bins of the individual variables n1 times n2. Add one more variable and you will get n1 times n2 times n3, number of bins. The whole point, the number of bins of an n-dimensional histogram is very, very large. A common situation in particle physics can be 10 discriminating variables, each bin in 10 bins, and this results in 10 billion bins. You will never populate such a histogram with the costly Monte Carlo events. So, this chapter will be about how to approximate the likelihood ratio as well as possible with the finite sample of Monte Carlo events. Numerical methods doing this are called MVA methods.